Good morning, everyone, and thanks for tuning in for another session of the ARC Coral Co seminar series. Before we get started with anything else, I'd like to acknowledge the Bindal and Wuguru Kaba peoples as the traditional owners of the lands and waters where we live and work here at the center and James Cook University, and honor their elders past, present, and emerging. I'll hand over to Patrick to give an introduction of our speakers today.
Hi, everybody. So today it's my absolute pleasure to introduce Zoë Lieb and Chris Roelfsema, who are working on the Allen Coral Atlas, which is going to be one of the coolest new tools for coral reef conservation out there. I first was introduced to them through work I was doing with the National Geographic Society. And when they told me about the Atlas, and it was just being rolled out at that point, it was a huge shock because I'd spent about half my PhD. Sorry, there's a blender going on in the background. I'd spent about half my PhD trying to work out how to use maps like these and how to find them and trying to piece them together from various sources. And then it was sort of like a silver bullet. Suddenly these came along and made the whole thing a million times easier. So yeah, I'm really excited to see what they have to say today. And without further ado, let's introduce.
Awesome. Thanks, Patrick. Hopefully everyone can hear me. Thanks to the Center of Excellence for having us present in the seminar series. Thanks also to Ian for organizing with us. And we're excited to share with you today about the Allen Coral Atlas, a new tool for coral conservation. I'm Zoë Lieb. I'm the project coordinator for field engagement with the Atlas team. And also presenting with me is Dr. Chris Roelfsema. Thanks, Patrick, for the introductions. Chris is with the Remote Sensing Research Center at University of Queensland, and he leads the mapping team for the Atlas. This co-author list is just a subset of the many people who work on the Atlas. It's funded primarily by Vulcan Inc., which was founded by the late Paul G. Allen and was inspired by his passion for coral reefs. Paul passed away in October 2018 after the start of the Atlas. And this partnership of coral reef scientists, universities, NGOs, and private entities also builds on the vision of the renowned coral reef scientist, Dr. Ruth Gates, who also passed away in 2018. So our project very much stands on the shoulders of their great contributions to conservation. I'm not sure this slide is changing. Chris, you wanna? Thanks, thank you. To familiarize you with our partnership, our team includes Planet, Arizona State University, the National Geographic Society, and of course, Vulcan, as I've mentioned. We all bring different components to the project, and our diverse perspectives of linking technology with coral reef science and management is a major strength of our whole team. And you'll hear more about each of the different partners later in a different section. Thanks. Yeah, next slide, please. And hopefully I haven't lost connection yet. Okay, I invite you to the interaction data, and I'll be presenting
Sorry, we don't hear you. Hello, everybody. Chris here. I'll just take over for a minute. Zoe's talking from the UK and I'm talking from Brisbane. So basically the Allen Coral Atlas is the idea to basically bring all kinds of monitoring and mapping parameters together in one environment. The idea is to bring the first ever high resolution map of all coral reefs in the world that are dynamically updated for the monitoring systems for all the shallow coral reefs. That's our mission to go to that. It started with the idea that currently there are some great products available that describe the outline of the reefs, or in some cases the geomorphic zonation. But the current UNEP layer that most people are using, if they look at large regional extent, is actually a result of a variation of different methods. As you can see here as some examples of the outline of reefs throughout the world. But also some reefs are not mapped, as you can see on the top one. So that triggered the first step of saying, well, we should actually try to create a consistent map of all reefs in the world. And it also shows us data gaps. For many countries, they don't have the funding or access or availability to get maps. An example of that is some of the work done in Myanmar by Fauna and Flora International. So they like more information of reef areas. And that's one of the aims that the Atlas try to achieve. So having given that introduction partly by Zoe, who possibly gets online better at the second part of the talk, we will go through what is the Allen Coral Atlas, how we make the atlas. Zoe or I will do a demo, and then we'll give some ideas of the atlas impacts, and then it's time for questioning. So what's the Coral Atlas? Well, most of you in Australia probably know Heron Island, and several of you probably have done research there. And this is just an example of one of the reefs that is visible on the Planet Dog imagery. It shows a high level of detail in those imagery. For Heron Island in the UNEP layer, this is the extent of the map of the reef on it, and this is the level of detail available. With the Allen Coral Atlas, we aim for Heron and all the reefs in the world to get this level of detail for geomorphic zonation, and this for benthic composition. With this data, we started this work, so some background. So part of this work comes from the University of Queensland, from the remote sensing team that started doing annual surveys on Heron Reef and developed methods to do coral reef mapping that was pulled out to the Capricorn Bunker Group with the help of the Great Barrier Reef Foundation, and then to the Cairns Cooktown sector, also with the help of the Great Barrier Reef Foundation. That triggered mapping of the whole Great Barrier Reef, which is in process for, as well. And that triggered also mapping all the reefs in the world, using our knowledge and gains over 20 years in regards to the mapping. But next to the mapping, we actually also include monitoring. And there's two main products coming out, and there's drafts of it now on the website. One is the brightening products, which looks at change in spectral signatures of the imagery. And I'll tell more in detail about that in combination using NOAA's coral reef reports. And then there's a turbidity product coming out, which shows quarterly turbidity over in the reef areas around the world. The advantages of the atlas are threefold, and each of these I will go through in the next section. So first of all, the global scale and consistency. So basically the reefs are done at a global scale between the 30 degrees latitudes. And the methods that we apply are consistent for every reef in the world. Yeah, so that's the main characteristic. We try to take so that it's comparable, and we use also the same classification schemes for that, which, as you will notice, can be challenging as well. Then the next step is that we actually use a high-resolution satellite image database from Planet Dog. And maybe some of you said, "Oh, but that's available on Google." And in some cases, it's even higher available on Google. But the difference is the images that we are using are a mosaic of the same type of imagery. So all Planet Dog imagery covering the whole Earth's surface. And then a really important point of the atlas as well is that it was aimed that the data is freely accessible. So the products that we will show and that the atlas delivers, anybody can get them. So that means the geomorphic, the benthic maps, the bathymetry, the monitoring products, and the imagery people can get access to. Next to that, especially the team of NetGeo is creating with NGOs tools, but also assist agencies throughout the world, NGOs or government agencies, to basically use the data sets and help improve conservation, protection, and monitoring of their reefs. And also to basically get feedback to see what areas are maybe not as mapped as good as we hoped, and to see if we can prove that in further versions of the maps. So, of course, on any mapping exercise, there will be, in any work, there will be limitations. And here's some of the four main limitations that we will highlight, so that everybody is aware that where you can use it and where you can not use it. So the first limitation is the water depth. Basically, the geomorphic maps, we map up to 15 meters deep and the benthic up to 10 meters deep. And it has all to do that the deeper you go, the harder it is to differentiate. And we know that there's large areas of coral reefs deeper, but at this stage, using airborne remote sensing, it's not possible to go much deeper on a global basis. So one of the depth limitations was also that we wanted to take care that we could apply the same rule everywhere in the world. So that's the depth limitation constraint. Then a biological constraint. As some of you know, if you look at corals and algae, we do know there are different plants, animals, when we work on them, when we do science on them. But if you look at the amount of light they reflect and how they reflect it over the whole wavelength, then you can see that those, what we call spectral signatures, are pretty similar, which makes it very hard for multispectral sensors, so sensors with only 4 to 5 sensitive bands, to differentiate them. Hence, coral and algae will be a similar class throughout. Honestly, I know that for certain reefs, I'm pretty happy to pull them apart because we now have a good understanding of those reefs. But again, we try to do our methods on every reef in the world the same way. And that creates one of these constraints. Then temporal constraints. So although the imagery we're using is provide almost a daily cover of the Earth's surface, we need low tide imagery and we need cloud-free and as less sun glint or waves as possible. So as a result, we work for the habitat mapping with a subset of imagery selected from the whole archive that goes over roughly a year basis, which basically means that the habitat map that we are creating for the world's coral reef goes over the period of 2018-2021. The brightness and turbidity are dynamic maps, and they will be updated based on the area where it's applied, but also on the imagery that are available for that area. But that's still in a work in progress as well. And then the spatial constraint. The mapping approach that we apply is applied to map reefs over a really large area. So here's an example of the Western Province in Solomons. That is more than 100 kilometers in length. And it's all different reefs around it and all different influences. So we try to get an approach that covers that whole area. And it works really well on this large scale. But it's also very clear that if you would zoom in into a really tiny little area of it, that you will see things that you're not completely happy with. And that has mostly to do with the choice of, okay, what kind of approach do we apply? But in general, because of this approach, we are making comparable maps for coral reefs. So give you that background on what's the atlas, what the Allen Coral Atlas is, some of the highlights, but also the constraints, I'll now talk you through the making of the atlas. And we use this beautiful graph that Emma Kennedy, who works in our team, has created, which basically shows the different components of this map, where we have different groups working together to to go through this process. And I'll talk you through. So first we have the imagery. That comes from Planet predominantly. And the Planet DOF imagery are basically covering one reef in a go, you could say, about 10 kilometers, one image. And it has between 3 and 5 meter pixel sizes. And that varies due to the way it's processed, which means that you can recognize features at a high level of detail on the reef. You can see jetties, you can see bigger boats, you can recognize them. And you can see different benthic features as well. If you put that in, the imagery is bought by Vulcan, and they provided the philanthropic organization, and they provided for the whole project. And I'll tell you a bit more about Planet in a second. Then you have Sentinel data, which is freely available and from the European Space Agency. That's radiometrically, it's a bit better, it's better quality, but it has a bigger pixel. And as a result, we can, because of the better signal to noise, we can actually create good bathymetry maps out of it. We also use Landsat to fill in gaps where we don't have any of the other data, for the bathymetry especially, not for the mapping. And in some cases, we use MODIS for atmospheric correction. Now you can see all these images have different areas that they capture and different level of details. So the Landsat image, you cannot pick up really small details where you can do that with DOF. And obviously drone data would be very nice for all the world's coral reefs, but that would be a big job. And we try to integrate it into any of our field components to use as well, because as we all know, drone data provides a high level of detail. So with that in mind, keep in mind that these are not maps, these are pretty images that look really great, but you can't do a quantitative or qualitative assessment from them, quantitative assessment. So if you look at the Planet satellite imagery, they cover the Earth's surface and they go around the Earth in such a way that they basically cover the whole constellation of 170 satellites on a daily basis, map the Earth's surface. There's also a SkySat sensor, which is a higher resolution sensor, which is also from Planet, which we use to zoom in into specific areas. And the quality of that sensor, the radiometric quality is also better, but it doesn't have complete coverage. The images together create this beautiful mosaic that we're working with. So those image data set goes to Arizona State University, which is led by Greg Esner, which some of you have heard, and his team looks at the image products. So first of all, we need to understand what happens with these products. So a sensor, a satellite or airborne, basically is a camera that picks up the reflected sunlight from the Earth's surface. But in the past, from going from the sun to the sensor, it gets absorbed and abstracted through the atmosphere. It gets inverted in a water column, and when it reaches the water column, and again absorbed and abstracted. On top of that, the water is moving, as we all know, or most of you know, I hope. There's tidal differences, which makes water deeper and shallower. There's currents, which mixes the water composition, and then it's waves, which creates sun glint at the surface as well. So basically what the Arizona State University does is peel back as much as possible and apply cloud mask to take care that we get as clean as possible images if there's clouds in it. And you get to a situation that instead of seeing images like you see on Google with clouds in it and some errors in it, we try to come to this clean mosaic of satellite images. It's not perfect, and I bet people have seen some errors in it, and we recommend to give that feedback to the Atlas, because our team at the Atlas will try to take care to that in next version that's corrected. The bathymetry is derived from satellite imagery. It's a relative bathymetry and gives us a bit of an idea what the shape of the Earth's surface is underwater, up to around 15 to 20 meters, depending on the water clarity. And we can use that in our mapping approach as well. Then, of course, with some of you know, I would always say that if you map or model something, you have to smell it. And this is the part where the National Geographic team and the University of Queensland team work together to get field data. This field data is not only field data they collect themselves, but it's also any data we can find of maps that include maps and field data over the last 10 years. And ideally, we go out everywhere in the field for every reef. But obviously with COVID that it's restricted now, but then even then it would be restricted anyway because of the amount of resources. So our team emails around and gets information of the different people and to see if we can use it and get agreements with them to work with it. To set location, we've been going to do these georeference photo quadrant surveys where we get thousands and thousands of photos divided over different reef systems so that we get a good idea what's there. Those photos, yeah, we do not only do it, we have also local teams, students and NGOs in different countries in the world having collected for us the same type of data. The method that we use for that are the geolocated photo transect surveys where a GPS is at the surface and a snorkeler or diver takes photos at a consistent distance from the surface that it represents the 1 meter footprint. That data, when there is sufficient there, will be used to automatically calibrate and validate. If there's not sufficient there, we do a process where we integrate it into a reference data set. So that's where we have all the input. We have the imagery, we have the bathymetry. We also derive some kind of wave product from an overall global wave product, and we have the field data. With that, we go into the mapping. Now, an important part of the mapping is that we actually know and agree on what we are mapping. And that's an enormous task that Emma Kennedy led in our team, where she basically pulled all the classifications that we use and existing one, reviewed them, and we came to a short list of classes in the dimorphic and benthic classification scheme. And it's not ideal because you try to draw a straight line through nature. What we're doing is we divide the satellite image, which is of pixels, into certain groups. So the benthic group, to just benthic for us is algae, rock, rubble, seagrass, and corals, and are mapped up 1 to 10 of meters. And then we have the dimorphic zonation, which is simply said are the lagoon, the reef crest, the reef flat, and slopes. But you can see more detail on the atlas. But this classification scheme is one of the important inputs of our mapping efforts as well. So with that information, we put all these input values together. So imagery, field data, our knowledge and experience on reefs, classification scheme, the satellite derived depth, and the wave height and slope, and a reference sample. So it's lots of different data. It's not just looking at the pixel, it's looking at our complete understanding of these reef systems. We use, which is also very unique, and for a lot of people, obviously don't realize it, that it's actually a low tide mosaic that we use. So there's so many scenes together that we can get a low tide mosaic, which makes it very easy to pick up things like reef crest, for instance. The data, because there's so much, gets analyzed in a Google Earth environment. And Mitch Lyons spearheaded that research, where he basically did all the research we've done over the years. He said, okay, let's see if we can do it in the Earth Engine environment, because it needs to be online processing so we get access to all data, but also that we can use the power of the Google Earth Engine, which is, we can't do this anymore on our desktop or on a laptop. The scripts are all on the GitHub. Anybody can access them, and there's 4 main modules: the data preparation. You imagine it like cooking. You have to prepare your ingredients. Then we do a first step, which is a random forest classifier, where we use the reference sample to train a random forest classifier and to get a dimorphic and benthic map. And then we do what we call an object-based cleanup, where we basically look to relationships. So for instance, reef crest, I assume most of you know, would not be surrounded by outer reef flat. On one side, it should have a slope. So we would do those kind of tests to check that and change that. We know that terrestrial reef flats should be an adjacent land. So if they're not, then it shouldn't be. On the reef crest, we wouldn't expect a lot of sand. So if something is labeled as sand, we usually turn it into one of the neighboring classes. And then, of course, there's an accuracy assessment as well for all the maps based on the reference sample. So we do that for the mapping regions, and we divided the world in mapping regions using Charlie Veron's ecoregions as a basis, and I think there's 180 ecoregions, and we made 28 of them. And how did we go to 28? Well, we basically looked at the different regions and the combinations, but we also looked at the satellite imagery and how the reefs are compared visually, and grouped reef systems that look similar or which would have similar challenges. And that comes up to this list of regions. You see also the small reefs. There's large areas in the world which have just a reef on its own and nothing more, and try to include them as well. Now, just for this, for many of you would know these people or have worked with them because they're all at UQ or even some are based at JCU as well. But to show that it's a combination of coral reef ecologists and habitat mappers, wave modeling, geomorphologists, coding, remote sensing specialists that forms the team at UQ, and of course PhD students as well. That's for the mapping component. I thought, knowing the history of your center and bleaching, I thought to also introduce you to this work. It's done by Arizona State University, where they basically try to create brightening maps. So what does it mean? Well, because of the enormous amount of satellite imagery, we have over a year's time a coverage of one reef many times. So by looking at the time frames of a year that is low sea surface temperature, so we don't expect bleaching, we select all those images and create what we call a baseline for it. And we say, okay, this is how it on average should look like. Then if an event happens, the imagery are compared to those, and that could trigger what we call a deviation of the baseline. And that could be suggested that there's a brightening happening. Obviously, some field work would help to improve that. But that's using the NOAA products in combination with the habitat mapping and the satellite imagery. So all the data and the products that are coming out are going through, once they produced, then they go up to the atlas on a temporary site, and the National Geographic team talks to local experts and they review some of the areas. Obviously, they can't review everything, but they review the maps. And based on that review, we maybe make some more correction for version 1 of the map, and then the map gets online and everybody can get access. That counts for the bathymetry, the geomorphic, the benthic, and for the brightness products when they're fully online as well. Currently, an example of the brightness of products is online for Hawaii. The idea of the atlas is that it brings back together the satellite imagery, the depth data, field data, and maps to basically help conservation, restoration, protection, and many other needs of these products. The Net Geo team and the biologists at Vulcan and also at UQ are working together to also advise NGOs or government agencies how the data sets can be used. So now we see if Zoe can give a demo. Zoe, want to go for it?
Hey, Chris. Can you guys hear me okay? How's this? No.
Yeah, we can
Hopefully
hear
you
you.
can hear me.
Yeah.
Great, thanks. I'll give it a try. Thanks everyone. Thanks for doing that, Chris. Awesome. And great. If I drop out, we can switch back. Yeah, so as you were hearing from Chris, the Atlas itself is the website holding all of these data sets that Chris has been describing. And I'm just going to do a quick demo to show you how to use it. First, this is our homepage. We recommend making a login. They are free and they'll allow you to access more features on the Atlas. Cool. And I've just picked a place in some islands for us to look at first. A few options. There is the NOAA Coral Reef Watch data layer available, and we've recently added a time selection option. So you can look back as far as October 2018 for the Coral Reef Watch, the different layers from Coral Reef Watch. So that can be a really helpful tool to visualize on the Atlas. You can also opt to not have satellite imagery on, lower bandwidth access. And there's also labels that are new. And I'll start looking at the benthic layer. And we're just going to select a nice area to that. Actually, you can look at the satellite first because it can look quite lovely. This might be an area you're familiar with. Possibly not.
Sorry, we don't hear you.
Off to help. Okay, am I back yet? I think it's hard. It's just too much for it to, I think. No.
Shall I take over?
Yeah, go.
Okay. So basically, if everybody can see it, it will be great. So basically here you see the Allen Coral Atlas. And as Zoe mentioned, you can see the base maps here. You can see on the right the different Coral Reef Watch products from NOAA integrated and go back in time. You can see the different satellite imagery for every reef in the world for a mosaic of 2018, 2019, 2020. These mosaics are the best pictures Planet could find, and it's a pretty picture mosaic. So it's not the same imagery we use for the mapping, because that's the low tide. You can find labels, and you can also find the brightness products, where currently it's only the version for Hawaii that can be viewed. The geomorphic and benthic maps, you can zoom around and you see the little colors already occurring on the reefs. And going from Tonga, you can zoom into reefs there, and slowly the maps will be visible for every single reef. So this is the geomorphic map coming up for this area. And then the benthic can go overlaid on it as well. You can see the legend coming up here. And so that's very clear as well. But this is Tonga, but I can go to another area in Fiji or New Caledonia, and now also the Solomons, to this area on the Solomons. And again, you're able to see those categories of those maps there. Here's the geomorphic, and in the same way you can look at the benthic. There's a whole description of the classification you can find online. Are this described? So this if you press on the eyes, then you will see that. Now the cool thing of the Atlas as well is that you can basically go to a little reef and actually sorry, that's not working. and then an analysis of what's there on the reef, of the different classes. Next to that, you can actually also download the data. You can first save an area, a test area. And then you can actually see in my areas, and you can see what you can download. So the things that you can download for free are the imagery, the benthic map, the geomorphic map, the quarterly turbidity, and the water depth. That will be prepared for you to download from you get an email where you can then get the zip file from. This is very small. You can only do it online for 100 square kilometers. But if you have a larger area, you can submit an outline for a larger area, and you can get, once you submit that, it will take a bit longer, but you would get data for that whole area back as well. And like Brianna said, you can combine it with the NOAA data, let's say degree heating weeks. That should come up. Oh, it doesn't come up. Oh, wait. That's interesting, of course. It's always with live. Well, yeah, that's of course. Oh, there it's. Oh, no, it's not coming. Well, basically for the region that could come up as well. Oh, there it is. We just didn't have enough heating weeks there. So here you can see that example, and you can zoom in on the maps and see those products. You can see also the blogs and science and methods which explain and frequently asked questions as well. All the areas are attributed, so you can find for every map we created, you can see also which field data has been used from which paper or which online document or which organization. So that's with the demo. So I'll go back to the presentation so that you guys see the presentation, I assume. Wait. Okay. Zoe, you want to go on this? It's not really happening.
I can't see your screen yet, actually. Okay, yeah, go ahead, Chris, or feel free to skip over this section too.
No, this is important section. So I will finish off this talk with the impact. So basically the field engagement team that is led by Helen Fox and others, I say, by Helen Fox and others are basically looking into expand the reach of the products and try to get more people involved. So for instance, we're talking now, starting to talk also with high schools and high school teachers, how they could use it in their classes as well, because students could do little exercises with the data sets. So that's on one thing, on the kids side, but NGOs can download it also. It's integrated in several programs like Mermaid from WCS, and other projects are happening as well. We try to take care that we increase the capacity for conservation sector by helping to utilize the tools and resources. So the Nature Conservancy, for instance, was funded by the Atlas team to basically create a lecture material which was introduced earlier. And then, of course, and engagement helps also to facilitate further data collection. So if you look at some of the impacts, then this is an example of how the data sets have been used. So here is Saipan, and the data has been used for local managed marine areas decision to discuss the scenarios that are there and basically talk with the different stakeholders while looking to these maps and zooming through what are the best scenarios, or to download the data and have a GIS specialist to work with the data set as well. On top of that, we get feedback from them for things that work and don't work, so that we can, in next version of the mapping or in updates of the atlas itself, the website, that we can basically improve them. Here's another example in Vanuatu, to basically where the maps were used to assess which reefs are vulnerable for runoff. So they created models for that to prioritize it. They looked at where sustainable aquaculture could be located. And they also looked at the restoration sites for seagrass and coral. And that's partly used in these kind of reports of those systems. Another example here, where we looked at how it can support countrywide analysis for whole countries, because the data sets are there, where you can look at the statistic on a region by region basis, how it works. And also to get knowledge about the different habitats and how they affect on one island group versus another island group. To, for instance, look at the marine spatial planning efforts such as in Vanuatu. The online products can be seen online and anybody can access them. Of course, one of the things the team has been working with is to try to take care that the bandwidth is right, not only in areas where there's good internet, but also in areas where the internet is not as good. Other examples is also the impact of disaster management. So here, another example for Vanuatu, where the satellite images could be used to assess if there's any damage on a larger scale or not. And similar to that is what went in the Seychelles. One of the reefs was hit by an oil tanker, and the maps were used also for that. So we developed capacity with our collaborators to basically with the online courses, so introduction to remote sensing of coral reefs, the Allen Coral Atlas, and of course the remote sensing toolkit created by the UQ team. And that's now available. Anybody can access that, and it's free. Training workshops, so the engagement team and the mapping team as well try to, on their symposia and conferences and workshops, to try to create additional workshops where we talk through the products of the Atlas and provide more input so that people can use them. And there are demo videos and YouTube and other online materials online. Till now, this is the progress of the mapping component. So the green areas are the areas that the first version of the maps are online. The red areas are planned, and the orange areas are where we're working on currently. By October 2021, we would have a first version of all reefs ready online, and we hope to continue improvements based on feedback that we're getting and additional data sets and improved imagery, because as I mentioned in the beginning, the SkySat sensor, which is also a Planet product, is a higher end sensor, and that knowledge of that sensor is used to improve the other sensors as well. So yeah, that gets us to the end of the presentation. So if you have any questions, please come forward, and otherwise email it to us or to the Atlas, and sign up for the newsletter. So yeah, any questions?